I want you to just close your eyes for a second. Think about last summer or, the summer before that. It's not just hot anymore, is it? It's that kind of heat that, like, sits on your chest. It feels thick.
Yeah, it feels heavy.
Heavy, yeah. It feels dangerous, fundamentally different from the heat you grew up with.
That visceral experience you're describing, I mean, that is absolutely what the data is showing us. But we're talking about something far, far beyond just uncomfortable weather.
Right.
We're seeing a globally catastrophic acceleration of warming.
And that is the story we are diving into today. We took this whole stack of sources you sent over, the climate journals, the economic proposals, all the satellite data, and they reveal an almost unbelievable paradox.
It really is a paradox.
The planet just hit the climate accelerator pedal, and the culprit, somehow, is our own success in cleaning up the air.
It sounds like science fiction. I know.
It totally does, but it's hard science reality.
So our mission today really is to unpack this sudden spike, this rapid removal of a shield we didn't even really know we had, and then figure out what it means for global warming and, critically, for the policy decisions that have to be made, like now.
Okay, so let's start with the facts. Let's ground this conversation. The Copernicus data, all the global temperature records, they are basically screaming at us.
They really are.
2024 wasn't just another warm year. It was unequivocally the warmest year in recorded history. I mean, since we started tracking this stuff seriously back in 1850.
And that isn't just, a record on paper. The data shows 2024 hitting a global average temperature of 1.6 degrees Celsius above the pre-industrial average.
1.6.
Yeah. That's just staggering. It means, for the first time, we officially blew past that critical 1.5 degrees Celsius guardrail, the one from the Paris Agreement.
I remember when 1.5 degrees was framed as this, far-off target for 2050, maybe 2060 if we were lucky.
Right.
The speed at which we got here is
it's
terrifying.
It is the speed that matters most. It's everything. If you look at the rate of warming over just the last 40 years, the global mean temperature is now increasing at a rate that's equivalent to 2.4 degrees Celsius per century.
Whoa, wait. 2.4 degrees per century? I need some context for that number. Before we started industrializing everything, what was the natural speed of change?
That's a great question. If we go back, say, 7,000 years before the 20th century, the global temperature was actually in a slight natural long-term decline.
It was cooling.
It was cooling at about 0.07 degrees Celsius per century. So we've taken a planet that was naturally cooling at a snail's pace, and in less than a century, we have cranked up its warming by a factor of over 35.
That is not a subtle change.
No. The acceleration is not subtle. It's a geological speed bump. It's a shock to the system.
And we are seeing the direct, immediate, and really dramatic consequences of that speed. I mean, I'm talking about the energy that's just powering our weather now.
Okay.
Look at the tropical storms we saw recently, Helene and Milton. They weren't just big storms. They rapidly intensified. They went from a tropical storm to a Category 4 or 5 monster in, hours, not days.
And that intensification is directly fueled by the atmosphere's appetite for water vapor. And this is the key: extremely warm sea surface temperatures.
The ocean heat.
The North Atlantic and the Gulf of Mexico became a literal hot tub. It was providing constant, limitless energy to these systems. When the ocean is that warm, the storms just drink the fuel. There's nothing to stop them.
And beyond the storms, we have to talk about heat stress, because just looking at a thermometer doesn't really capture the danger anymore.
Exactly right. The sources really focus on something called the Universal Thermal Climate Index, or UTCI.
Okay.
That index is far more meaningful to you as a listener because it doesn't just measure the dry air temperature. It factors in humidity, wind speed, radiation.
So it's about what the heat actually feels like to your body.
It's what it feels like, and it's what determines how quickly your body can actually cool itself. So as the oceans absorb more of this energy, we get more water vapor in the air, greater humidity,
Right.
and that makes that 35-degree day feel physiologically like 45 degrees. The UTCI is a measure of pure danger, and that danger is spiking globally.
Which brings us to the core mystery of this whole deep dive. If greenhouse gases have been rising pretty steadily for decades, why this sudden, dramatic, almost parabolic spike in 2023 and 2024? It felt like someone just stomped the gas pedal when we thought we were just kind of rolling along. The standard climate models didn't fully see this coming.
It's not a feeling. It's a fundamental shift in the planet's energy budget. We track this thing called the Earth's Energy Imbalance, or EEI.
Okay, so EEI, break that down.
Think of the Earth as a bank account, but for thermal energy. The EEI is the net energy gain. It's the difference between the solar energy coming in and the thermal energy radiating back out to space.
So we're depositing more energy than we're withdrawing. How much more?
We measure it in watts per square meter. In the first decade of this century, the EEI was already pretty concerning. It was sitting around 0.5 watts per square meter.
Okay.
But in the past decade, that number has doubled. It's now roughly 1.0 watt per square meter.
It doubled.
It doubled. That doubling means the Earth is soaking up heat twice as fast as it was just 20 years ago.
Doubling the energy gain. Okay, let's put that number, 1.0 watt per square meter, into a context that doesn't just sound like physics jargon. What does that kind of sustained energy gain actually equate to?
Well, if you take the total surface area of the Earth, that 1.0 watt per square meter of net energy gain is equivalent to continuously running something like 600,000 of the largest nuclear power plants we have on Earth.
600,000.
All of that energy just perpetually dumping into the planet's system, Q147. That's where all the extra fuel for the stronger storms and the hotter oceans is coming from. The energy bank account is just skyrocketing.
And this doubling, this sudden acceleration of energy absorption, it demands an answer, right?
Yeah.
If the greenhouse gases are the steady pressure on the gas pedal, then something must have failed on the braking system.
Exactly.
And that brings us directly to the second part of our deep dive. The villain, or maybe the deeply problematic anti-hero in this story.
The invisible shield.
The invisible shield. The sources make it really clear that the climate system has been balanced very precariously by two enormous opposing forces for the last 100 years or so.
That's right. On one hand, you have the long-lived warming agents, CO2, methane, nitrous oxide, the usual suspects.
Right, the greenhouse gases, they trap heat, they stick around for centuries, they're the fundamental driver.
And on the other hand, you have the short-lived aerosols.
Aerosols, so that's the tiny particle soot, sulfates produced mainly by burning fossil fuels in industry, power plants, and critically for the story, by using really dirty shipping fuels and biofuels.
And their effect is the complete opposite of CO2's. They reflect incoming sunlight directly back into space. They literally brighten the planet, acting like a massive temporary mirror or a sunshade.
That's the mechanism behind that term global dimming, right?
Yeah, that's it, exactly.
So we created pollution aerosols that killed people immediately, but we simultaneously generated greenhouse gases that caused long-term warming. And by some strange, terrible coincidence, the quick-acting pollution was masking the slow-acting warming.
It is the perfect definition of a Faustian bargain. It truly is. We modernized and industrialized the world by burning coal and oil, which pumped out the CO2 that started this long-term warming.
Yeah.
But at the same time, that very same industrial activity created sulfates and soot that reflected sunlight and provided a cooling benefit, temporarily offsetting some of that warming.
So we got the immediate benefit, economic growth, and like a hidden climate problem without worrying about the future consequences.
We got the present benefit, yeah, without any regard for the future, compounding climate consequences.
It's hard to reconcile that. I mean, we are talking about an ethical dilemma of the highest order here. Because while this shield gave us decades of delay on the climate consequences, the shield itself was made of deadly particles.
That is the painful truth. While these aerosols provided a temporary climate service, they are toxic particulate matter. This pollution is responsible for millions of premature deaths worldwide every year.
From what, like strokes and lung disease?
Strokes, heart disease, respiratory illnesses, yeah.
Yeah.
So the cleanup of this pollution was never optional. It was a necessary public health intervention, essential for saving millions of lives.
So if we didn't clean the air, millions would just continue to die every year. But if we did clean the air, we knew we would be taking down the sunshade and exposing the true underlying rate of global warming.
It's a tragic trade-off.
A tragic trade-off that we were forced into by decades of just not dealing with CO2.
The sources really reinforced just how potent this shield was. Way back in 1992, researchers concluded that the magnitude of the cooling effect from human-made aerosols was similar, but opposite in sign, to the warming effect from greenhouse gases.
So they were almost canceling each other out for a while.
They were, yeah, for time.
So if we visualize the climate system like a car, the engine, the GHGs was getting bigger and the gas pedal was being pressed harder and harder. But the handbrake, the aerosols, was also being ratcheted up at the same time.
An extremely effective handbrake. The best scientific estimate is that the cooling provided by this temporary, filthy shield masked about 0.5 degrees Celsius of warming.
Half a degree.
Half a degree. If we hadn't had that aerosol masking effect, the planet would likely be approaching 2 degrees Celsius of warming today, rather than the 1.6 we just hit. That zero point 0.5 degrees of mass warming is the deferred payment on our Faustian bargain.
And that payment comes due with lightning speed. That's the mechanism that defines this acceleration, right? Why do GHGs persist, but aerosols just vanish?
That's the core scientific difference that defines this crisis. Carbon dioxide is incredibly long-lived. If you release a ton of CO2 today, about 40% of it will still be in the atmosphere 100 years from now, warming the planet.
It's a centennial timescale.
Exactly. Aerosols, by contrast, are short-lived. They exist primarily in the lower atmosphere, where they get washed out really quickly by natural processes, rain, snow, gravity, within days or a few weeks.
So when we clean up the source of the pollution,
The shield essentially vanishes in the blink of an eye.
so we've created a system where the heating element is durable, but the temporary cooling element is disposable. Flip the aerosol switch off, and all that mass warming is instantly and rapidly revealed.
Which is exactly what happened.
So we didn't intentionally start a global climate experiment to stress test the planet.
No, not at all.
We did it purely for public health reasons. But that air cleanup, especially since about 2010, is acting exactly like a controlled experiment, showing us the true rate of warming. So let's look at the evidence for this unmasking moment.
The scientific community has been able to pinpoint the acceleration because two massive simultaneous pollution reduction efforts, one global, one regional, took place almost at the same time, removing different parts of the shield.
Let's start with the one that cleaned up the world's oceans. IMO 2020. This is the International Regulation on Shipping Fuel.
Correct. The International Maritime Organization, the IMO, that regulation went into effect on January 1st, 2020. And it was a massive global change.
What did it do?
It required ships to reduce the maximum sulfur content in their fuel dramatically, from 3.5% down to 0.5%.
Wow, that's a huge cut.
It's a huge reduction, over 2/3 in sulfur dioxide, or SO2, emissions from the entire shipping industry.
And before 2020, those shipping lanes were basically creating their own reflective highways in the atmosphere, weren't they?
They absolutely were. If you looked at satellite images over busy ocean corridors, especially the North Pacific and the North Atlantic, you could clearly see what looked like bright white lines following the paths of the ships.
The ship tracks.
Exactly, ship tracks. Those sulfates from the dirty fuel acted as perfect cloud condensation nuclei, or CCN.
Cloud condensation nuclei, the tiny seeds that water vapor needs to condense into a visible cloud. Okay, let's use the analogy engine here because we need to understand how pollution actually changes the cloud itself.
Good idea.
Let's go with a daily life analogy. Maybe something from the kitchen.
Perfect. How do we make the invisible shield visible?
Let's think about baking. Or maybe making whipped cream. Imagine you're trying to make a perfectly whipped meringue, which is basically a thick, white cloud of sugar and egg whites.
Okay, I'm with you.
The pollution, the soot, and the sulfates from the ships, it acts like the tiny grains of salt or the acid that helps stabilize the meringue. When those particles, the pollution seeds, are numerous, they allow the water vapor to condense into lots and lots of tiny little droplets.
And many small droplets make for a very bright surface.
Exactly. Lots of tiny droplets scatter sunlight incredibly efficiently. The cloud becomes brilliant, white, dense, and highly reflective, like a perfectly peaked, bright white meringue. That is high reflectivity. That's cooling. That dense white cloud acts like a powerful cooling lid over the ocean.
So what happens when we remove the pollution?
When the air gets clean, like with IMO 2020, and we remove those aerosol seeds from the ship exhaust, the water vapor still condenses, but it has to condense onto fewer available particles. This means it forms fewer, larger water droplets. And these bigger droplets don't scatter light as efficiently. The cloud structure thins out, it becomes less bright, less dense, and much less reflective.
So we basically made our meringue thinner and less effective as a sunshade by cleaning the dirt out of the atmosphere.
We did, and this isn't theoretical, right?
Yeah, not at all. Studies show that immediately after the IMO 2020 regulation took effect, there was a striking, measurable reduction of these bright, reflective ship tracks. And here's the undeniable connection. The areas that saw the largest reduction in ship aerosol emissions, the North Atlantic and parts of the North Pacific,
Let me guess.
are the precise areas that experienced the most shocking spike in anomalous sea surface temperatures right after 2020.
So you're saying that removing that reflective lid allowed the solar radiation that was previously being scattered back to space to just hit the ocean directly.
Precisely. The Ceres satellite data, which measures the Earth's net radiation budget, confirms this. We saw an immediate, measurable increase in absorbed shortwave radiation in those specific oceanic regions starting in 2020. That is the physics in action. The ocean started soaking up the energy that the aerosol shield was previously blocking.
So we had the immediate global scale cleanup over the oceans, but we also had a simultaneous regional industrial cleanup happening in East Asia, which was another massive source of SO2.
Case study 2. This involves countries like China, which, in response to their own severe smog issues, implemented massive effective air quality improvements. Since around 2010, they've achieved a dramatic 75% decrease in sulfate aerosol emissions.
That is an enormous reduction in industrial pollution in a very short amount of time.
It is, and the modeling studies suggest that the East Asian cleanup contributed a large fraction, up to 0.05 degrees Celsius per decade, to the observed global warming acceleration.
So you have a 1-2 punch.
A 1-2 punch. Global shipping cleans up the marine atmosphere, and East Asia cleans up the industrial atmosphere, both dramatically reducing the aerosol shield at roughly the same time.
The planet was just hit with a step change in energy absorption. This simultaneous removal is what makes the current acceleration so unprecedented and so rapid compared to previous warming periods.
It is, and the speed is further confirmed when we look at natural aerosol experiments, volcanic eruptions. They function as a sort of natural control group, showing us just how transient this aerosol shield is.
The classic example being Mount Pinatubo in the Philippines back in 1991.
Pinatubo was massive. It injected roughly 20 megatons of SO2 high into the stratosphere, and that led to a clear but brief global cooling of about 0.3 degrees Celsius.
But how long did it last?
Within 2 years, that effect was gone. The atmosphere scrubbed it clean. It proved the point.
And the more recent example was Hunga Tonga Hunga Hapai in 2022.
Yeah, Hunga was different. It injected far less SO2, maybe 1 megaton, but it also injected a massive amount of water vapor high into the stratosphere. And water vapor is a potent, albeit short-lived, greenhouse gas.
Ah, so it was a mix of effects.
Right. The modest cooling from the aerosols was actually partly offset by the warming from the added water vapor.
Yeah.
But both events, Pinatubo's huge cooling and Hunga's complex balance, confirm the principle. Aerosols are a fleeting 1 to 2 year shield. When the source stops, the cooling stops instantly.
Okay, so we've established the mechanism. The simultaneous cleanup from shipping and East Asia created the perfect conditions for the record-breaking heat of 2024. Now, what is the science telling us about the true magnitude of that unmasking? I mean, how much warming did we actually reveal?
The quantification studies are, well, they're compelling, and they confirm that this pollution shield was more powerful than many of the established models had accounted for.
Really?
Researchers who modeled the combined reduction in SO2 from China and international shipping since 2005 estimate that this removal may account for approximately 0.14 degrees Celsius of additional warming today.
Wait, 0.14 degrees Celsius? That is a massive chunk of the increase we've seen in the last decade. It explains a huge fraction of that acceleration we talked about earlier.
It certainly does. And if you look specifically at the IMO 2020 regulation, one study focused purely on that shipping cleanup.
Just the ship.
Just the ships. They concluded that removing the sulfur dioxide from the shipping fuel alone likely increased the planet's temperature by 0.08 degrees Celsius.
Nearly a tenth of a degree added to the global thermostat in just 3 or 4 years.
Yep.
It's incredible that a public health success could have such an immediate, drastic, and frankly terrifying climate consequence. This is why the warming rate is now measured at over 0.2 degrees Celsius per decade, the fastest sustained rate we've ever observed.
And that accelerated rate means that breaching the 1.5 degrees Celsius Paris Agreement target is now. It's not a possibility for the future. It's practically locked in for the 2030s, if not sooner.
But this acceleration has a huge implication beyond just the temperature record itself, right?
Yeah.
It's forcing a significant, uncomfortable disagreement about the fundamental physics of our planet.
Exactly. This is the scientific controversy, and it's all about climate sensitivity.
Right.
The interpretation that decreasing ship emissions caused such a major, rapid acceleration suggests that human-made aerosols were providing a much stronger cooling effect than the IPCC's traditional estimates had assumed. Some researchers are suggesting the aerosol forcing in the North Atlantic was twice as powerful as previous IPCC assumptions.
Why does that difference matter so much? It's just modeling, isn't it?
It matters because of climate sensitivity, or ECS. ECS is probably the most important single number in climate science. It asks a simple question. How much does the Earth's temperature ultimately stabilize if we double the atmospheric CO2 concentration from pre-industrial levels?
And the standard answer has traditionally been around 3 degrees Celsius of warming for doubled CO2.
That's been the best estimate, the consensus number that policymakers often use. But if this invisible shield, the aerosols, was masking more heat than the models accounted for.
It means the CO2 we've already emitted has caused more heating than was apparent.
Precisely. Therefore, the planet's underlying sensitivity to greenhouse gases must be higher than that traditional 3 degrees Celsius estimate.
So we realized that the CO2 engine is actually a bigger engine than we thought, because the brake we were unknowingly relying on was more powerful than we assumed.
That is the perfect summary. The older generation of global climate models, the GCMs, they sometimes struggled to realistically simulate these complex dynamic processes like cloud microphysics.
They just couldn't see it properly.
They simplified how aerosols interact with low-lying clouds, especially in critical regions like the Southern Ocean. But as cloud modeling has become more sophisticated and we're incorporating these complex shortwave low-cloud feedbacks, several of the modern models are indeed finding a higher climate sensitivity.
So cleaning the air didn't just warm the planet. It performed an instantaneous reality check. It forced climate science to admit that the system is far more sensitive or volatile to GHGs than we were modeling even a few years ago. It revealed a hidden danger.
And that hidden danger forces us to confront the tipping points we're now approaching far, far faster than anticipated.
So we've established the Earth's energy imbalance has doubled. We've unmasked the true warming, the high global temperatures we are seeing now, especially the sea surface temperatures. They're establishing a new, higher baseline.
Right. We're not going back to 2019 levels of warmth, even as natural cycles like El Niño fade.
This new reality means we are dangerously close to locking in a global temperature excess of over 2 degrees Celsius, and that trajectory increases the danger of hitting major Earth system tipping points.
The points of no return.
Exactly, where continuous warming pushes a system over a threshold and the resulting change becomes self-sustaining and irreversible, even if we eventually cut all our emissions.
Yep.
So what are the two most critical tipping points that this accelerated warming is bringing closer?
The first one is the instability and potential collapse of the West Antarctic Ice Sheet, or WAIS.
Okay.
It sits on bedrock that is hundreds of meters below sea level, which makes it extremely vulnerable to melting from warmer ocean water circulating underneath it. The warming trajectory we're on right now puts us into temperature ranges similar to the Eemian period, the last interglacial when WAIS is believed to have partially collapsed.
And the consequence of that collapse is measured in meters of sea level rise, not centimeters.
Exactly. We are talking about several meters of sea level rise over the next few centuries. Not 30 centimeters, but 3 or more meters.
The impact on every major coastal city, from Miami and New York to Shanghai and Amsterdam, that would be globally transformative and permanent.
It would be. The second major concern is the ocean circulation system, the North Atlantic Overturning Circulation, or AMOC.
The AMOC, we hear about this a lot, but why is its potential shutdown such a big deal?
The AMOC is like the planet's conveyor belt. It pumps warm, salty water north and deep, cold water south. It's a critical regulator of heat distribution for the whole planet.
Right.
But as the Arctic warms and the Greenland ice sheet melts, fresh water is injected into the North Atlantic, and that slows that overturning process down.
It's like adding too much fresh water to a salty mix.
Exactly. And recent analyses and sophisticated modeling suggest that the slowdown is already dramatic, and that a complete shutdown of this circulation system could occur as early as the middle of this century under our current accelerated emissions scenario.
So if that conveyor belt stops, what does that actually feel like for us in terms of weather?
It would dramatically alter global climate patterns. Europe would experience a bizarre regional cooling, especially in winter, because the mechanism bringing northern warmth would just cease.
But what about the rest of the world?
Well, more broadly, it would lead to catastrophic shifts. Drought in the Sahel region of Africa, massive changes in the South American monsoon, and extreme sea level rise along the eastern coast of North America.
Wow. So the acceleration is real, the planet is more sensitive, and these consequences, imbalance, they're approaching faster than any traditional model predicted. This means that rapid GHG emissions reduction, while still the #1 priority, it might not be enough on its own anymore.
That is the consensus emerging from the source material. We need fundamental policy changes to get emissions to zero rapidly, and then we need to think about additional actions to temporarily manage the Earth's current energy imbalance.
Okay, let's start with the fundamental solution that economists seem to favor for deep, rapid, sustainable emissions cuts: the carbon fee and dividend.
This is widely considered the most efficient market mechanism. It involves putting a rising fee or tax on carbon pollution right at the source, the mine, the well, the import point.
So it creates a clear price signal.
A clear, predictable price signal that pushes businesses and consumers away from carbon-intensive stuff and toward clean energy innovation.
But the key is the dividend part, right? Because people hear carbon tax and they panic about rising prices.
The genius of the dividend model is that 100% of the fees collected are returned directly to the public as equal monthly dividends.
That was fair.
It addresses the fairness issue immediately. It's revenue neutral to the government, and studies show that the majority of low and middle-income families would actually break even or come out ahead.
Because they tend to use less energy but get the same dividend as a high-energy user.
Exactly. It's efficient, it's equitable, and it drives rapid decarbonization. That's why it has such broad support across economic disciplines.
That seems like the logical long-term policy path. But given that the climate system is now demonstrably more sensitive, and we are staring down tipping points that could hit within 30 years, like the AMOC shutdown, we might need an emergency brake.
We might.
And that brings us to the really radical option: purposeful global cooling, or solar radiation modification, SRM.
This is the controversial discussion that this sudden acceleration forces us to have. SRM involves speculative, temporary techniques designed to reduce the risk of climate overshoot and buy us time to achieve those massive, deep emissions cuts.
But isn't solar radiation modification fundamentally just treating the symptoms while ignoring the root cause, the CO2? Why would researchers even consider such a risky path?
You hit the skepticism exactly right. It does not address the root cause, which is the accumulation of GHGs. But the reason it's being discussed now is risk reduction. If we know the AMOC, or the West Antarctic Ice Sheet, is approaching a collapse threshold far faster than we thought, a temporary intervention might be necessary to pull the climate back from the brink while the long-term solution zeroing CO2 is implemented.
It's a risk mitigation strategy.
Against catastrophic, irreversible change, yes.
And what are the main techniques being modeled?
The two main types are stratospheric aerosol injection, or SAI, which basically mimics large volcanic eruptions like Pinatubo by injecting reflective materials into the upper atmosphere to scatter sunlight.
Okay.
The second is marine cloud brightening, or MCB, which aims to make low marine clouds brighter and more reflective by spraying fine sea salt particles into them.
So we're essentially trying to rebuild the aerosol shield we accidentally removed, but in a targeted, reflective, and non-toxic way.
That's the idea.
We're attempting a controlled application of the sunshade we just realized we had, but the caveats here must be massive.
They are enormous. First is not a substitution for cutting CO2. If we start SAI and then stop, say, due to international political disagreement, the warming that was being masked would instantly emerge. We call it termination shock.
Termination shock.
The temperature would spike violently, far faster than the natural environment could ever adapt.
Which would be catastrophic for biodiversity and human society.
Exactly. And furthermore, SRM is fraught with uncertainties about regional impacts. Injecting aerosols, for example, could disrupt delicate climate patterns, potentially altering the location and intensity of monsoons or causing unintended regional droughts or floods.
So we might solve one problem only to create several others.
That's the fear. It forces these global governance questions that we are nowhere near ready to answer.
It seems like the biggest environmental success of the last decade, cleaning our air and saving millions of lives, came with the terrifying price tag of accelerating the global climate crisis, forcing us to consider truly radical, risky policy options simply to buy ourselves a few decades of time.
The sources are presenting humanity with two clear, hard truths. We need to implement fundamental economic policy like carbon fee and dividend immediately.
Right.
And because the clean air revealed a climate system far more sensitive than we thought, we might be forced to consider risky, temporary intervention to stabilize Earth systems.
Okay, let's unpack this core insight one final time. This deep dive showed us that cleaning up deadly air pollution in shipping and East Asia was our generation's great environmental achievement, but it came with an immediate, terrifying climate cost. It revealed the true power of rising GHGs and accelerated our planet straight into that critical 1.5 degree zone.
And this acceleration exposed a climate system that is far more sensitive to CO2 than we previously assumed. This means that existential threats like the AMOC shutdown or multimeter sea level rise from the West Antarctic Ice Sheet are now approaching faster than any model predicted, compressing the timeline for effective action.
This raises an important question, then. Given the immense challenge of achieving deep and rapid global emissions cuts, and the growing evidence that aerosol cleanup has exposed a climate system far more sensitive than we thought, we have to ask, Is our biggest long-term risk still the CO2 we refuse to cut? Or is it the possibility of massive, irreversible Earth system tipping points that are now approaching so quickly that we can no longer afford to wait for emissions cuts alone?
What do you prioritize when the clock is ticking this fast?